Welcome to this Advanced Explainer Masterclass. We're diving deep today. Have you ever wondered if the universe literally has a hidden code, constantly running in the background to correct its own glitches? Well, today, we're going to look at exactly how pure numbers and geometric dimensions are fundamentally linked. We're getting right into the Adelic Langlands program. It's an incredible framework that actually reframes and completely resolves a massive open problem in geometric group theory. So let's get into it. Here's our roadmap for today. We'll start with the Eilenberg anomaly, then we'll cross the Adelic bridge. After that, we'll literally see how math squeezes topology, define the Adelic dimension identity, map all of that to spacetime curvature, and then wrap things up with universal quantum error correction. All right, section 1, the Eilenberg-Ganea anomaly. So the Eilenberg-Ganea conjecture looks at what you could call a central mathematical crime. The question is, can a group's algebraic footprint actually mismatch the minimal physical space it needs to be built? Just look at this equation right here. It's essentially asking, is there a group out there where its cohomological dimension, think of that as its algebraic shadow, is strictly 2, but its geometric dimension actually needs a 3-dimensional space to exist without collapsing it on itself? Now, in classical math, this is a huge topological blind spot. A 2-dimensional complex can host these wild, irregular cell attachments that basically fool our algebraic invariants, making it look like you absolutely need a 3rd dimension just to smooth everything out. Moving on to section 2, the Adelic Langlands bridge. This comparison beautifully illustrates a massive paradigm shift. Instead of just counting cells or hunting down static, geometric counterexamples, which is what classical topology does, the Adelic Langlands program pushes us into Adelic spectral geometry. We're totally changing the game here. We start treating the group's topology as the spectrum of a generalized Dirac operator, and this operator is acting on an infinite-dimensional Adelic Hilbert space. It's wild. What used to be seen as just some geometric mismatch is now elevated to a full-blown global information theoretic anomaly. Now, the really crucial point is how we actually track this anomaly. We map the group G to a continuous Galois representation over the Adel ring. Take a look at the J-theory clamp shown here. If our geometric dimension suddenly drifted up to 3 while the algebra was stuck at 2, the system just wouldn't have the algebraic rank to support it. It would be mathematically starved. In this framework, a hypothetical 3D topological defect registers explicitly as a local ramification event. It forcibly injects a non-zero local conductor exponent, which is what we call f sub p, where f sub p is strictly greater than 0, right into our representation. Okay, section 3, squeezing topology with math. So how do we evaluate 2 independent group operations interacting? We use the Rankin-Selberg convolution. We take 2 representations, let's call them pi1 and pi2, along with their local Satake parameters, which hold their internal eigenvalues, alpha and beta. The local p-adic convolution factor you see here is literally the inverse determinant of their tensor product. Looking at the formula, we're calculating a degree n-squared polynomial that rigorously tracks every single cross-channel eigenvalue combination. And guys, this isn't just abstract math. This is the exact calculation of the cross-entropy generated when these geometric structures intertwine. It's quite literally math actively reading physical stress. Now, let's integrate that Rankin-Selberg convolution on a global scale. Focus your attention on the exponent on the right side of this main equation. It's the regularized logarithmic derivative of our L function evaluated right at the physical 40 mass scale where s equals 1. This is doing something incredible. It acts as a strict energy clamping mechanism. Because this cross-entropy is tightly regulated by prime numbers, these groups can't just intertwine with some random arbitrary phase mismatch. This arithmetic squeezing actively prevents infinite dimensional inflation in the vacuum. If a 3D anomaly even tried to form, this derivative would wildly diverge, and that forces the continuous metric to flatten out instantly. Which brings us to section 4, the Adelic dimension identity. This right here is the absolute resolution to the Eilenberg-Ganea anomaly. The equation shows that the geometric dimension must be less than or equal to the cohomological dimension, plus the sum of those local conductor exponents f sub p, all modulated by the global wave harmonics of the Adel ring. But here's the absolute magic of it. The global functional equation demands strict local global conservation. Having an unramified baseline forces the global conductor n to equal exactly 1. And because n is 1, the system is mathematically forbidden from hosting any local ramification whatsoever. Therefore, f sub p is strictly 0. The boundary condition completely collapses, snapping the geometric dimension down perfectly. So, geometric dimension equals cohomological dimension, which equals 2. That 3D anomaly, mathematically crushed. Section 5. curvature, and spacetime geometry. Let's link this to the physical world. When these interacting group structures max out their entanglement, they hit a saturated limit, and this unfolds in 3 very specific steps. Step 1, this saturated cohomological bound activates local ramification currents at the finite primes. Step 2, we bring in the Grothendieck random rock push forward. I know, it's an incredibly dense mathematical tool, but it basically acts as a translator. It takes that internal, discrete arithmetic stress and maps it directly onto our continuous 4D spacetime base space. And finally, step 3, this causes the macroscopic metric to undergo non-abelian conformal warping. Literally, discrete arithmetic stress is bending continuous 4D geometry. And here is the exact literal expression of that bending, the emergent 4D Ricci curvature tensor components. Look really closely at the term k sub a of n in this equation. The overlapping non-commuting phases actually freeze the Satake eigenvalues, locking them to this fixed arithmetic coupling constant. So this k sub a of n factor essentially becomes a universal gravitational coupling constant. In this framework, gravity scales strictly based on exactly which prime numbers are actively processing the network's geometric entanglement. Which leads us to a seriously profound physical implication. When fields try to exceed that cohomological bound, say if they try to leak into a 3rd geometric dimension, the arithmetic energy overflows. By Einstein field equivalence, this overflow of arithmetic stress manifests macroscopically as a stress-energy tensor. Just think about that for a second. Gravitational mass isn't just stuff floating out there. It is literally maximally compressed arithmetic data that is desperately trying to bridge topological dimensions. Absolutely wild, right? All right, our final section, Section 6, Quantum Error Correction. We can actually map all of this directly onto a topological quantum code. The classifying spaces of the groups we've been looking at aren't just abstract ideas. They literally act as the physical substrate for fault-tolerant topological qubits. We assign physical data qubits to the 2 cells in the complex, using vertex and edge stabilizers to track all the boundaries. The core principle here is that the absolute alignment between the cohomological and geometric dimensions forms a logical mathematical shield. It's the exact boundary preventing any phase slip leakage into unprotected 3-dimensional states. But what happens if an error actually tries to occur? Well, enter the Satake syndrome operator. Think of it as a multi-qubit measurement circuit. It evaluates the inverse characteristic determinant of the local Hecke eigenoperator. Now, if our space is unramified and perfectly safe, this operator evaluates to exactly 1. But if a stray 3D cell attachment error tries to corrupt the baseline, it acts as a local ramification event. The conductor immediately spikes, and the syndrome operator instantly reads a non-trivial eigenvalue. It catches the glitch red-handed. Here is that full self-healing cycle in action. Step 1. A stray phase slip attempts a 3D geometric leakage. Step 2. The Zodiac classifier instantly detects this non-zero syndrome. Step 3, the global functional equation attempts to integrate this, but because macroscopic reflection symmetry cannot accommodate local, isolated anomalies, it immediately triggers Step 4. And in Step 4, the global L function aggressively clamps the conductor back to n equals 1, forcing that local exponent right back to 0. The 3D anomaly is mathematically crushed back down to 2D. This all brings us to a truly stunning conclusion. The reason the macroscopic geometry of our universe remains a smooth, stable, 4-dimensional space is because it's a globally synchronized, self-correcting arithmetic web. The universe doesn't leak or drift dimensionally because it's actively, constantly running this exact homological error-correcting routine in the background. Our continuous dimensions are held in this unyielding balance by these discrete, unramified Adelic networks. Which leaves us with a truly mind-bending question to ponder. If the very continuous dimensions of our universe, literally the space we move through every single day, are actively stabilized by discrete number-theoretic codes, what other physical laws that we just take for granted are really just mathematics actively correcting itself? I hope this explainer has completely reframed how you see the intersection of algebra, topology, and our physical reality. Until next time, keep questioning everything.